Hey guys! So a classmate asked, how do you solve the following problem? A 1.00 liter container holds 1.06 moles of H2 and 1.57 moles of CO at a temperature of 162 degrees Celsius. At this temperature, the following reaction occurs. 2 H2 gas plus CO gas produces CH3OH. After equilibrium is established, analysis shows that 0.200 moles of CH3OH is in the container. Calculate the Kc. To start off, let's first understand what type of problem this is. The question itself is asking us to solve for Kc, which is the equilibrium constant for concentration, where the products and reactants of a reaction are expressed in terms of molarity. The other equilibrium constant, Kp, differs in that products and reactants are expressed in terms of partial pressures, measured in atmospheres or millimeters of mercury. Remember that equilibrium constants are expressed as products over reactants, with Kc having the concentrations of products over the concentrations of reactants, and that concentration is denoted with brackets. In this question, we'll be using a Rice table to help us solve our Kc. Rice stands for reaction, initial, change, and equilibrium. So if we look at our question, we see that we already are given a reaction, represented by the equation 2H2 plus CO produces CH3OH. Now, for our initial, we will put in the initial values of our products and reactants before equilibrium. Note that in a Rice table, only concentration and pressure values can be placed inside it. So, for the initial values of our reactants, we have to convert them from moles to moles per liter. Luckily for us, since the container only holds 1 liter, then the concentration of the initial values will be the same as the moles of the initial values. Since 1.06 divided by 1 is still 1.06, and 1.57 divided by 1 is still 1.57. CH3OH will have an initial value of 0, since before equilibrium it does not have any value. Don't be tricked by the 0.200 moles given in our question. That's the amount of CH3OH after equilibrium, and so it should not be in the initial line of our Rice table. Next, for change. We don't know exactly how much each compound will change after equilibrium, so for each compound I'll write an X underneath it. Now, what we do know is that this change is stoichiometrically based on the above coefficients, so we will bring down each coefficient from the original equation next to the X. Finally, we must decide what direction our reaction will shift. Which way we shift for our table will always be towards the 0, since there's nothing over there and it must gain something to reach equilibrium. So we will add a plus on the product side and minuses for our reactants, since our reactants must lose some value to gain some value for our products. Finally, for our equilibrium, we will just combine together all the information we have from I and C for each of our compounds. So in our equilibrium line, we will write 1.06 minus 2x, 1.57 minus x, and x. Now, we cannot solve for the concentrations for any of our values of equilibrium because of this x. And without any equilibrium concentrations, we can't solve for our equilibrium constant. Luckily for us, the 0.200 moles of CH3OH is actually helpful. This is our equilibrium of CH3OH, which is the same thing as X. Remembering that our 0.200 moles of CH3OH are not expressed as a concentration, we must divide it by the volume of 1.0 liters, which will get us the 0.200 moles per liter. So if we plug in 0.2 for X in the equilibrium line, we get the concentration of H2 at equilibrium to be 0.66, the concentration of CO to be 1.37, and the concentration of CH3OH to be the same 0.200. Now that we have our equilibrium concentrations, we can solve for Kc. With Kc equaling the concentration of products over the concentration of reactants, our Kc expression is the concentration of CH3OH over the concentration of H2 squared times the concentration of CO. Note that the 2 exponent on H2 comes from the coefficient in the chemical equation given to us, with CH3OH and CO having their own implicit coefficient and exponent of 1. Plugging in our equilibrium concentrations, we get 0.200 moles per liter over 0.660 moles per liter squared times 1.37 moles per liter, getting our final Kc value to be 0.335. I hope this video helps you to understand equilibrium problems and rice tables.